So welcome to the first seminars in spring. So because of COVID-19, we're gonna present the seminar series via Zoom. This is unfortunate. The committee members are Emily, Hector, John William, and myself. So if you have any questions or suggestions to improve the seminar series along the way, please let us know. And today we have Srijan Sengupta with us. And Srijan is our own faculty member, and he graduated in 2016 from UIUC. And before joining us, he spent 4 years at Virginia Tech. And he has a very broad research interest, including big data, computational statistical methodology for network data, and also bootstrap related methods. Today, he is going to give a presentation about Hodor, stands for holdout design for online randomized experiments with lurking variables. For the next 50 minutes, also, he will give this talk. Before we dive into this, just a little housekeeping. So this session will be recorded and it will be available on YouTube. And all participants, except for the speakers, should mute the microphone during the seminar. And also, please participate in the seminar. So if you have any questions, you can unmute yourself, or you can send the questions to the chat box. With that, I will hand this over to Sengupta. Srijan, whenever you are ready.
Okay. Okay. Can you all see my screen?
Yeah.
Okay, great. Thanks, Shu, for the introduction. And thanks to Shu, Emily, and John for organizing this seminar series. And for those of you who are surprised to see that I am at NC State, I don't blame you. This has been a weird fall semester. I have been at NC State since fall, but I haven't really been able to see anyone. So thanks for turning up for my talk. So before I start, there is something I realized like 10 minutes before starting this talk, when I was putting this date on the slide. So today is Jan 22nd, 2021. And pretty much exactly 1 year back, on Jan 23rd, 2020, I also gave a talk at NC State as part of my job interview. And we know how 2020 turned up from there. So this is your chance to bail if you want 2021 to be better than 2020. Just fair warning. Okay, so just another kind of distraction before I get into the more serious part of the talk. And apologies to those of you who have attended one of my pandemic talks before, because this is a stale joke that I have been making at all my pandemic talks. So the theorem says that it's mathematically impossible to make slides for virtual conferences since there are no flights to take. We all know that we make our slides on the flight to the conference venue, and in an online conference, you cannot do that. So therefore, you will never make your slides, and therefore you will never be able to give your talk. Now, and since the topic of today's talk is lurking variables, the resolution of this paradox is actually contextual to that. So why are we still able to give talks at virtual conferences? Well, because in this theorem, we are missing an important lurking variable. We are missing an important covariate. So since you are no longer visiting cool places, you can now stay up the night before and make the slides. Otherwise, you would have gone out in the town and had fun. So this year, my conferences were at Cyprus, at Greece, in London, and in China. So you miss all these wonderful places to visit, and therefore you can just stay up the night before and make your slides. Okay. Here are my partners in crime and two of NC State's finest. Jonathan Stolrich is assistant professor at NC State. Nick Larson is a PhD student at NC State. And like my main reason for showing this slide is that if you like anything about this talk, all the credits are due to me. If you hate anything about this talk, you know whom to blame. Okay? But seriously, I mean, this has been a really fun collaboration. As you will see, this is mostly based on experimental designs and stuff, which is something I know nothing about. So John initiated this collaboration, and initially I was coming at it from the networks perspective. John was coming at it from the experimental design perspective. And I think we ended up integrating it in a really cool manner. Okay, also at any point during the talk, feel free to unmute yourself and interrupt me if you have a question to ask. Okay, so let's start with A/B testing, which is very popular in today's internet economy. So to statisticians, an A/B test is basically just what we always knew as a controlled experiment. So the point is that we want to compare how two variants, we call them A and B. So there's a factor, typically a factor. So there's a factor with two variants A and B, and we want to compare how these two variants affect the user response differently. So henceforth, I'm just going to use test and control for the two variants of this factor. Okay, so why not just use the paired sample paradigm that is kind of very, very well known to statisticians? Well, one thing about A/B tests is that typically the response from a user cannot be observed twice. Okay, so you cannot do like a before and after, and that is in the nature of the experiment. So it's like the user gets destroyed once you use it in the experiment, once you experiment upon it. So you simply cannot assign both variants to the same user and then observe the two responses. A very large variety of important real-world settings fall into this paradigm. For example, vaccine trials, something that we are going through right now. So in vaccine trials, you might have a vaccine candidate and a placebo, and you want to know whether the vaccine candidate is doing better than the placebo. So those are the two variants, vaccine and placebo. In online services, I mean, for example, the common websites that we use, like Wikipedia or LinkedIn, all these websites, they're constantly changing themselves. They're constantly adding new features, and the way they test whether these new features are useful is through A/B testing. Same with social media. So for example, Facebook, Twitter, all of them are constantly adding new feature, and they want to know whether the new features are going to increase engagement, and they use A/B testing for that. Government agencies do A/B testing. Political campaigns use A/B testing. Okay, now here is, so we'll start with kind of, and I'm going to assume that at least some of you know nothing about A/B testing. So I'll start from the very basic stuff, 1958. So what I'll go over is maybe the first, 30, 40 years of A/B testing, which is more from a classical statistical perspective. And then the next 10, 15 years of A/B testing, which is more from a computer science and machine learning perspective. So this was at the very core of A/B testing, the so-called stable unit treatment value assumption. In short, it's called SUTVA. So this says that in order to carry out an A/B testing reliably, you must have this assumption satisfied that the response from any user is unaffected by the treatment assignment of every other user. So if you are someone in this experiment, your behavior is completely independent of what's happening to everyone else. So does this hold in practice? Let's look at some of the examples that we talked about in the last slide. So here's a silly example. suppose you are carrying out a vaccine trial, but on the entire US population. Okay? Now, you have been randomly chosen to receive the placebo, but you do not know what other people have received. Now, just think of kind of the silly situation where you are the only person in the world to receive a placebo, and everyone else in the world has received the vaccine, and therefore they are now immune from the disease. Okay? So in that case, even if you have received the placebo, you cannot get the disease because there's no one else to get it from. On the other hand, if you have received the placebo while some other people have also received the placebo, clearly that increases your chances of getting the disease. Okay? So this is a silly example, of course, because vaccine trials are not conducted on entire populations. But let's look at a more realistic example. Let's look at like actual COVID-19 vaccine trials where members from the same household are recruited as participants in the trial. Okay? Now, suppose you are a trial participant and you have received the true vaccine, but you have another member of your household who is also a trial participant. Now, if that member has also received the vaccine, that means your chances of getting infected are much lower. Whereas that other member, if they have received the placebo, your chances of getting vaccinated or of getting infected is now much higher. So clearly your outcome, whether you get infected or not, depends on whether this other trial participant also gets the vaccine or the placebo. Similarly, in a classroom setting, if intervention is given to certain students, it can affect the other students in the same class. So clearly the SUTVA does not hold in most of the important scenarios where we want to do A/B testing. So this led to, historically, this led to the notion of network spillover. So what is network spillover? So network spillover is a phenomenon that in practice, SUTVA gets violated, and therefore users are affected by the variant that is assigned to their neighbors. So here's kind of an example, and similar to vaccine trial examples and classroom examples. So suppose a social media organization is considering whether to add a messenger service to their platform. Okay? So this would be an addition to their platform where you can send personal messages to other people who are friends of you. So here the test variant is messenger, the control variant is no messenger. That is, some users will receive the messenger, some users will not receive the messenger. And the response is user engagement. So the company wants to know, if you receive the messenger, how much time are you spending on the messenger? Now, clearly, if you are an user and you have received the messenger, but you do not have any friend who have also received the message, okay? In that case, you cannot use the messaging service. So you can only use the test variant if not only you have received the test, but also some friends of you have received the test. Okay? So there is clearly a network spillover effect. That is, it matters whether my neighbors or friends get the test variant or the control. All right. So let's kind of start mathematicizing some of these concepts just to, be able to talk in terms of parameters and models and numbers. So let's start with a very simple and kind of a toy model, really. So suppose we have n users and yi is a response variable, and yi is equal to alpha plus gamma xi plus a noise epsilon. So here alpha is the intercept. So that is just there. It's not really a parameter of interest. Xi is a binary variable. So if you were put in the test variant group, xi is equal to 1 for you. If you are in the control variant group, xi is equal to 0 for you. Okay? And gamma is the direct treatment effect. So what does this mean? So this means that for an user who have received the treatment, the test variant, yi is alpha plus gamma plus some error. For an user who has received the control, yi is alpha plus the error. And clearly this model satisfies SUTVA, because if you look at this model, yi is only affected by what happens to user I. What happens to all the other users has no bearing on the model for yi. All right, now the primary goal of A/B testing is to estimate what is called the average treatment effect, in short, the ATE. So what is the ATE? Think of the universe where everyone receives the treatment. So in a universe where everyone receives the treatment, the expected response will be this: expectation of yi given xi equals 1. We will sum this over all I from 1 to n, and we will take the average. So this first term is the average response if everyone in the universe receives the test variant. As opposed to, consider the universe where everyone receives the control variant. Okay? So this is where now we are interested in knowing the expectation of yi given that xi is equal to 0. The difference between these two is the average treatment. Okay? So, and this point is kind of easy to gloss over, so I'll just reiterate this again. It's important to remember that when considering the average treatment effect, we want to compare the universe where everyone receives the treatment versus the universe where no one receives the treatment. Okay? So because that truly measures the effect of the treatment. All right, now under this model, under this simple model, you can easily see that the expectation of yi when xi is equal to 1 is alpha plus gamma, and the expectation of yi when xi is equal to 0 is simply alpha. So the average treatment effect here is just gamma. We are going to call this the direct treatment effect because we already know that there can be an indirect treatment effect as well. Okay, so here is kind of a very classical common sense statistical design to estimate the average treatment effect. So we are going to call this random uniform design. We are going to split the n users randomly into two groups of equal size. And then the AT estimator is the average from the first group. So this is the average over the group for which xi is equal to 1, less the average over the second group where xi is equal to 0. Okay? So under model 1, remember that the only difference between xi equals 1 versus xi equal to 0 is that the gamma parameter gets turned on or off. Okay? So the group where xi is equal to 1, that will have an average of alpha plus gamma. The group where xi is equal to 0 will just have an average of alpha. So the expected value of the estimator is going to be gamma. This is the variance. So everything is hunky-dory here. Okay? You can estimate the average treatment effect using this simple design and this simple estimate. Now let's try and understand what happens when SUTVA is violated and network spillover happens. So now we have this model where the response is alpha plus gamma xi. So gamma is still the treatment effect, but now there is an additional spillover effect happening. And this is given by delta times Ti. So what is Ti? Ti is the proportion of my friends who have received the test variant. So think of the messaging service, right? So I have access to the messaging service, but if no one else among my friends have the messenger, then I cannot use it. On the other hand, if all my friends also have the messenger, then I'm going to use that a lot. So Ti, if all my friends have also received the test variant, then Ti is going to be 1. If none of my friends have received the test variant, then TI is going to be 0. Okay? So what this basically is saying is that YI is of course affected by whether user I receives the treatment or not, but it's also affected by what proportion of my friends receive the treatment.
I have a question here in this
Yeah.
Construction of this TI. In what aspect do you observe this random variable TI from the data? So I'm interested in saying, like, do you ask your friend that whether you got messenger or not? So do you get it visually from the data?
Yeah, that's a great question. Okay, so what you need here is that you need the entire adjacency metric given by AIJ. Okay, so the data now consists not only of observing what a user's response is, but the experimenter, the person who is doing the analysis, also needs to know how users are connected to each other. So they need to know the entire adjacency.
Okay.
But I think to answer kind of the implicit question that you are asking, the user does not have to be explicitly aware of how many of my friends are getting the test. Okay.
Okay.
It's something that gets implicitly factored in, because like if you go on Facebook and if you see your friends messaging you, you are going to message them back. For this, you do not need to know how many of your friends also have the messaging service. So similarly, in a world where everyone is vaccinated, you automatically get the spillover protection from other people getting vaccinated.
Okay.
You individually do not need to know how many of your friends are vaccinated. Okay.
Makes sense. Yeah.
But great question. And we are actually going to come back to that in more detail later in the talk. Okay, so what happens now? Under this model, where there is not only a direct effect, but also a spillover effect, the average treatment effect is now, so again, remember that we are comparing two universes, a universe where everyone receives the test, where everyone receives the vaccine, versus a universe where everyone receives the control. So in a universe where everyone receives the test, expected value of yi is going to be alpha plus gamma plus delta. Because since everyone is receiving the test, ei is going to be 1 for everyone in that universe. Okay? So that is the treatment effect from the test. And now in the control universe, where no one receives the test, yi is just going to be alpha plus epsilon, because xi is going to be 0 for everyone, and ti is also going to be 0 for everyone because no one receives the test. Okay? So the average treatment effect now is gamma plus delta, and this is what happens. I mean, so a lot of work in the last decade has been dedicated to this, that there is this additional spillover effect delta that was being ignored under SUTVA.
Excuse me?
Yeah.
Yeah, may I ask a question about the spillover effect you define?
Sure.
It seems to me the TI you define is a summation over all individuals you select who receive the treatments. And when you do the average treatment effect, it seems the I's or J's individual will be double or multiple counted when you do calculate the TI. For example, say the first individual, for the first and the second individual may also have the common friend, and this common friend will be double counted for the spillover effect. And I'm wondering how to deal with this.
Yeah. So yeah, that's a great question. So think about it this way: if you and I,
yes,
if the two of us, if we have a common friend who has been vaccinated,
yes,
then we get this, both of us get the spillover immunity from that fact.
Yeah.
Right. So therefore, in this model, yes, that person who has been vaccinated should be counted twice, both for my response and for your response.
Okay. And the, oh, I see. So so the spillover effect essentially kind of corresponds to the density or the dense of the network, right?
The density of the network only among the test group.
Yes. Yeah.
Yeah. So it's like so if everyone gets vaccinated, then it's the same as the entire population. But yes, it's certainly related to the density.
Cool. Thank you.
Great question. Thank you. Okay. Any other questions or comments? Okay. So this is what happens to the average treatment effect when there is network spillover. Now, in addition to the direct treatment effect, which is gamma, we also get a spillover effect, which is given by delta. And the more eagle-eyed of you would have noticed that we are not following the order of the Greek alphabet here. So it should be alpha, beta, gamma, delta, right? So there's a beta missing, but that's going to come into play pretty soon. All right. Now, what happens to our classical random design when there is spillover effect? So as before, we are just going to randomly split the users into test and control. And we can only use the same estimator as before. So I'm just going to take the average over the test group and the average over the control. Now, this is what happens. Let's go back to this model. Suppose users have been randomly allocated into test and variant, 50% in each group. What is going to be TI for someone in the test group? So TI is a proportion of your friends who receive the test variant. So if users are being randomly assigned into test or control, then your neighbors are also being randomly assigned into test and control. And therefore, on average, about 50% of your friends are going to receive the test, and about 50% of your friends are going to receive the control. Okay? What that means is that under random uniform design, for the group that is in test, they will have alpha plus gamma and 0.5 times delta. Okay? Whereas for the group that is in control, it's alpha, there is no direct treatment effect, but the same 0.5 times delta. Okay? So basically, again, think of the vaccine trial example. If there is a network spillover effect, the immunity that you get due to the spillover from your friends who have been vaccinated versus if you are in the control group, then the immunity you would get from your friends who have been vaccinated is the same. It cancels out. So if you are a clinical trial participant, you do not get any spillover effect, right? Because among your friends, there are going to be about 50% who have received the vaccine and about 50% who have received the placebo, and these two spillover effects cancel each other. So therefore, the estimated ATE is going to be approximately gamma in this case. And so this simple design now has a bias, which is equal to delta, which is the spillover effect. And this is not surprising. We knew that this simple design only works under the SUTVA, and SUTVA is validated here. So there is going to be a consequence. Okay? So this was pointed, this fact really became prominent around 2007-8 or so. And over the last 10 years or so, a lot of work has been done to address this problem. Our talk today is not about this problem. The talk today is about the overemphasis that has been given to this problem and how that has led to worse consequences that has been ignored. So this problem has been solved to some extent, and I'll go over how this problem has been solved, and then we'll talk about the real problem. So we are still in Act 1. Okay, so this is a picture from JPAL. So here is the reason why random uniform design is a bad idea in the presence of the spillover effect. So think of this red group being the treatment group and this green group being the control group. So everyone who is in red is receiving the treatment and everyone who is in green is receiving the control. Okay? Now the problem is that, as you can see, there's this red guy right next to this green woman and they can interact. Similarly, there's this treatment user right next to this control user, they can interact. Okay, so if this was a vaccination design, you can see that the fact that this person has received the placebo is going to affect what happens to these people. So this is the problem. So this spillover will happen when you have a design like this, which is random. How to solve this? This is how you solve it. Okay? So what you do is you choose a group of people who mostly talk to each other and put them in the treatment group. You select the remaining people who also mostly talk to each other and put them in the control group. Okay? So now there is still a little bit of spillover happening. So there is some spillover between this person and this person, or between this person and this person. But the spillover is much less than before. Okay? So so this is kind of just an intuitive idea. I'm going to show you kind of more pictures and more math. All right. So this is where network clustering comes in. So this is just, I mean, think of a network which is very well clustered, and we can implement some kind of well-known community detection algorithm to identify these clusters. Okay? So here is the basic idea. We take the network between users and we partition that network into several densely connected clusters like these. Okay? Then remember that in random allocation, we were basically looking at a user tossing a coin and deciding randomly whether that user should get allocated to test or control. Okay? Here we move that randomness to the cluster level instead of the individual. So having obtained the clusters in the first step, what we do is, instead of randomly assigning individual users to variants, we assign each cluster randomly to a variant. So for example, the blue group might receive the test. The yellow group might receive the control, and so on and so forth. So why does this help? Because this ensures that users in the test group are likely to have friends who are also in the test group and vice versa. So again, I'm going to show this mathematically in a second. Actually, let me go back to the model for a second. So this is our model, right? Now, if you indeed have the users tightly clustered, what it means is that suppose I have received the treatment, okay, and I belong to a tight cluster, and everyone else in the cluster has also received the treatment. Therefore, TI is likely to be close to 1 for me. On the other hand, if I am in a control group, then most of my friends are also likely to be in the control group, which means TI is going to be close to 0 to me. Because remember, TI is the percentage of people who have been vaccinated. Okay, so just for people who are more comfortable with the mathematical description of this, this is how it plays out mathematically. So we have one group that gets assigned the test. We are taking the average of them. We are taking the average of the second group that gets assigned the treatment. And now for the first group, for the test group, the average response is like alpha plus gamma plus T bar 1 delta. And this T bar 1 is the average fraction of neighbors of testers who are also in the test group. Right? So if I am someone who got the vaccine, then how many of my friends also got the vaccine? And T0 is the average fraction of neighbors of controls who are in the test group. So now the bias, so this is the expression for the ATE now, and this is the bias. And now if you indeed have very tight clustering, then T bar 1 is close to 1. Okay, because what that means is that if you think of the blue cluster being assigned to treatment, then take an average blue node, what percentage of their friends are also in the blue node? 100%, right? So in that case, you will expect T bar 1 to be close to 1 and T bar 0 to be close to 0. This is why there is still some bias, but if the network is friendly enough, that bias almost goes to 0. Okay, so good. So this has already been solved. There's nothing new here. This is basically things that have been happening over the last 10 years. So here's what we found out. This is where our work really starts. What happens when you have lurking variables? So lurking variables is something that statisticians, economists, social scientists have always considered. But perhaps people in the machine learning community, computer scientists, they have not really thought about lurking variables so much. And maybe that's why it has not been considered so far in this literature. So what are lurking variables? Lurking variables are unobserved user features which can manifest in two ways at the same time. So these are variables which can influence how the user responds to a test or a control. And these are also variables that influence how the user connects with other users in the network. So these variables have a dual role. They influence both network formation and response itself. So what does that really mean? So here's some examples. So think of educational attainment in a professional network. Okay? So think of something like LinkedIn. So people who have PhDs are probably more likely to connect to other people who have PhDs, right? So educational attainment clearly influences the way users form connections in a professional network. At the same time, suppose LinkedIn is carrying out some kind of A/B testing, and users' response to a change is also likely to be influenced by educational attainment. So something can be really too complicated, and highly educated people are probably more likely to use that feature than others. Think of political ideology in a social media network, like Twitter, right? So if you are closely aligned politically with another user, you are more likely to be friends with them. So political ideology clearly influences how you form connections. But political ideology also influences how you respond to a change in Twitter, for example. So for example, if Twitter has a new fact-checking feature, your response to that is probably going to be driven by your political ideology. Think of genetic predisposition to something like COVID-19. Okay? So if you are genetically predisposed to COVID-19, that increases the chances that you are going to be infected. But that also means if you are genetically predisposed, your family members are also likely to be genetically predisposed. So genetic predisposition is associated with the contact network, people you are living with, and it also affects whether you are going to be infected. So what happens when you have lurking variables in a network and you are carrying out an A/B test? So here's a network that we constructed. So in this network, the size of nodes is proportional to the covariate value of the user. Okay, so think of this, the covariate value as something like age. So larger the dot, higher the age. So this is what happens, and this is also a bit nuanced. So let's take time to kind of get this. We have taken a network where there is a lurking variable, and we have carried out community detection on that network. Okay? Now, for example, when you see blue nodes, those blue nodes are all nodes that belong to the same cluster or community. And when you see yellow nodes, the tiny ones or the green ones, they also belong to the same community. So same color means same community. Now here is the thing to observe. The blue nodes are generally of larger size, whereas the yellow nodes are generally of smaller size. Okay? So what this means is that you have this one cluster, the blue cluster, which generally has higher values of the lurking variable. And you have another cluster, the yellow cluster, which has low values of the lurking variable. So if you compare these two clusters, you are not randomizing with respect to the lurking variable. You are getting two very different distributions of the lurking variable when you consider these two subpopulations. Why does that matter? So let's first look at what is the true average treatment effect and how our old designs perform in the context of lurking variables. So this is the same model as before, where we have now added the effect of the lurking variable, and now beta comes into play. So Zi is the lurking variable. We consider that as a continuous variable. Without loss of generality, we assume that this has mean 0, because if it has a non-zero mean, that just goes into the intercept. And beta is the size of the effect of the lurking variable. Okay. All right. So what is the ATE here? So remember that we have to consider the two universes. A universe where everyone receives the test and the universe where nobody receives the test. The universe where everybody receives the test, the average response is going to be alpha plus beta Z bar plus gamma, because xi is 1 for everyone, plus delta because Ti is also equal to 1 for everyone. So this is the average response in a universe where everyone receives the test. Then we have to consider the universe where everyone receives the control. So that's going to be alpha plus beta Z bar. Okay? So there is no gamma xi because there's no test. There's no delta Ti because no one receives the test. So now what we have to notice here is that the beta Z bar cancels out in the two cases, right? Because the lurking variable affects user response in the same way, regardless of whether it's test or control. So the beta Z bar cancels out, and therefore the average treatment effect is the same as we have seen before. It's gamma plus delta, where gamma is the direct effect, delta is the spillover effect. Okay? So the ATE is the same, but what happens to the estimators of the ATE? Let's start with random uniform design. Just two equal groups. Now the average in the first group is likely to be alpha plus beta Z bar 1 plus gamma plus 0.5. So all these terms are the same as before, other than this new blue term, which is due to the lurking variable. Okay. Now, since we have randomly assigned users to the two groups, the average value of the lurking variable in group 1 and the average value of the lurking variable in group 2 are likely to be the same. They should just cancel each other. Okay. And therefore, this cancels out. The estimated ATE has the same expectation as the previous case, where we did not have a lurking variable. So what this tells us is that because we have used random allocation, the classical, the much maligned, the so-called outdated uniform design is actually immune to the effect of lurking variable. Okay? So it still has a bias. The same bias is had before, which is equal to delta, the network spillover effect. But it does not suffer any additional disadvantage when there is a lurking variable in the mix. Now let's look at what has been proposed over the last 10 years, which is network clustering based design. So we have the same expression as before. Z bar 1 is the average value of the lurking variable in the test group, and Z bar 0 is the average value of the lurking variable in the control group. But now these are likely to be quite different. Because let's look at the picture once again. So what you are going to do is you are going to put the entire blue cluster into the test group and the entire yellow cluster into the control group. So the Z bar 1 you see is going to be the average value from the blue group, which is much larger, whereas the Z bar 0 is going to be the average value from the yellow group, which is much smaller. What this means is that now you are going to have an additional source of bias, which happens because you have not used random allocation. Okay? So now we have a problem with network clustering based design. Okay, so so now we are in Act 2. So this is the chart sheet that we are going to present against network clustering design. So this is a new allegation, something that we have found. We have found that NetClus design is heavily biased if a lurking variable is present. Another new thing which we'll talk a little bit about in a second is that the network must be fully observed for network clustering to take place, because you have to cluster a network. Something that was already known but is still an existing issue is that unless the network consists of perfect components, right? I mean, so even more perfect than this. I mean, it has to. So this is like already close to perfect, but imagine even if these small connections were not there. So it is only under that perfect condition that NetClus can estimate the spillover effect correctly. Unless you have perfect components, it will even have a bias coming from the spillover. Okay, so now how can Hodor help us? And I'm going to, so this is going to be a bit mathy because I wanted to describe the whole thing, but I mean, write the whole thing down so that you can read it if you want, but I'll also explain this. So our basic idea is to use holdout design. Okay, so think of it this way. We see that random design has a problem because random design cannot estimate the spillover effect. We also saw that network clustering has a problem because it cannot adjust for lurking variables. If I can correct one of these imperfect solutions, which one should I invest in? We are saying that we should invest into the classical so-called outdated random design because there we have some hope of improving. The network clustering design is really hopeless because there's no way we know what's happening with the lurking variables because we never observe the values of the lurking variables. So here's the basic idea. We randomly assign N0 users into the control group, and the remaining users are all going to receive the test variant, but not all of them at the same time. Okay? So the remaining users are going to be randomly assigned the test variant in 2 stages. The stage 1 group has N11 users, and the stage 2 group, the holdout group, has N12 users. That's really the crux of our idea. Now the experiment is going to happen as follows. In stage 1, the users in N0 are given the control variant, and the users in N11, that is the first stage of the test variant, the users in N11 are given the test variant, and the remaining users, the holdout users, are not included in the experiment at all. We collect the data from these 2 groups. Now in the second stage, we give the test variant to the holdout users in N12. Okay? And then we collect data from this group. So we have an initial vaccine and placebo group, but we have a buffer group that we do not use in stage 1. We first vaccinate the first stage and give placebo to the first stage. We collect data from them, and then we are going to give the test variant to the holdout users in a second stage. So this sounds kind of strange and weird, right? So why and how does this work? And again, this is very mathematical, but I'll try to explain it. So think of think of just the first term, right? So that's the first term looks like something we had before. It's the average response from the test group minus the average response from the control group. We know what is the problem with this. The problem with this is that it can capture the direct effect, but it cannot capture the spillover effect. So how do we capture the spillover effect? The only way to capture the spillover effect is by having two subgroups of the text group, y12 bar and y11 bar. So we have two subsets of the test group, and these two test groups have different levels of spillover happening in them. When the first group receives the vaccine, only a small fraction of vaccines have been given. So the spillover effect is less. But when the second group receives the vaccine, they are getting the spillover effect from the first group as well as the second. So that is crucial here, that we create a second group which has more spillover than the first group. And once we do that, this coefficient is simply a linear interpolation to correct for the difference in the spillover effect in the two groups. Okay. So I'll just, and this is kind of writing it out in kind of mathematically. So I think this is probably something that's hard to get if you just stare at it, but you'll have to take my word for it that this works. Okay, how to optimize this? How to come up with the optimal design with this idea? Okay, so how to choose N0, N11, and N12. So N0 is the number of users in the control group. N11 and N12 are the first stage users and second stage users. So I'm not going to show you a theorem. But basically what we do is we can write down the variance as a function of these parameters and then minimize them. So one thing that's interesting is that once you do it, the optimal design that comes out is heavily unbalanced. And another interesting corollary is that the variance of the optimal version of Hodor is about twice the variance of classical random elevation. So if you compare Hodor with the classical uniform design, there's a bias variance trade-off here. Hodor adds some variance because there are now two smaller test groups instead of one big test group. So the sample size is less, due to which we have more variance, but it removes bias. So this really ties up with kind of some cool and kind of intuitive statistical principles. Okay. Numerical performance. So this is not really, I mean, I'll come back to this slide in a second after showing you the actual picture. So we looked at three cases. And here we are looking at the box plot of errors. So we have three competitors. We have the uniform design, we have NetClus design, and we have Hodor. Okay? And this is the box plot of errors from the three designs. We considered three cases. The first case is where there is no lurking variable, but there is a network spillover effect. So this first case is what people have been focused on these past 10 or 12 years. They have been looking at situations where there is network spillover. So what happens when in this case? In this case, uniform design does poorly. This was expected because remember that uniform design cannot capture the spillover effect at all. Since there is a spillover effect, uniform design is going to have a bias. NetClus design is supposed to correct for the spillover bias, and it does that to some extent, but not fully. Okay? This is because, as we said before, NetClus can completely correct for the spillover bias only when the network consists of perfect components, which are completely separate. Other than that, there is going to be some interaction between the test and control groups, and that is going to add some bias. And this is Hodor. So note that in this case, there is no lurking variable, but still Hodor has zero error, right? Because it actually does a better job of correcting for the spillover effect than the network clustering design. Now let's look at the second case where there is no network spillover effect, but there is a lurking variable. Okay? So in this case, uniform design now does quite well, because the only problem with uniform design is that it cannot capture the spillover effect. Now that there is no spillover effect to capture, it does well. NetClus now does rather poorly, because there is no network spillover effect to correct for, and it's suffering the consequences of there being a lurking variable. And Hodor once again does well because it can capture the effect of the lurking variable. And finally, we have a realistic scenario where we put both of these things together. So there is now lurking variable as well as network spillover. And now Hodor still does well. NetClus does pretty much as well as before. And here is uniform. Okay, so to come back to the chart sheet against NetClus design, a new allegation was that it is heavily biased if a lurking variable is present. A known allegation was that unless the network consists of perfect components, it has a spillover bias too. We can see that Hodor has corrected for both of these problems. There is a second problem which Hodor has not still corrected, that is the network must be fully observed. So this is really Act 4, where we are now going to extend Hodor to the case where you have not even observed the network. So there is a network spillover effect, and you have to estimate that when you cannot even see the network. So I'll just kind of motivate why this is important and then go into the results in the interest of time. So why should we consider this case? And this really connects to the very good question that Sholil asked at the beginning of the talk. An implicit assumption of network clustering is that the network of users is fully observed and therefore it can be clustered. So just like the SUTVA assumption is actually validated in many cases, this implicit assumption also gets validated in many cases. So for example, you could have a situation where the network is actually unknown or uncertain. So suppose there is a new feature being added to the Google search page. You do not really know how the network between users works there. So you cannot really, I mean, it's not like Facebook or LinkedIn where you can see how the users are connected. Similarly, think of vaccine trials where you have a placebo group and a vaccine group, but you do not really know whether the trial participants live in the same household or not. Okay? So one case is where the network is indeed uncertain or unknown. The second case, I think, is more nuanced, but even more crucial. The second case is where you think you know the network, but you actually do not. So because spillover actually happens through influence, when the behavior of one user influences the behavior of another user. Now, we might think that we know the friendship network. So for example, on Twitter, you know that a user follows a certain person. A user may follow 1,000 other people, but they are not equally influenced by the actions of those 1,000 people. They are likely to be more influenced by the actions of so-called influencers or celebrities than other people. So even when you think you know the network of user connections, you might be missing the actual influence network, which is different from the friendship network. Okay? So the short answer is that in this case, NetClus, I mean, previously we saw that NetClus has errors. In this case, network cannot even be implemented because there is no network that you can cluster. The good news is that, and I'm going to skip over the methodological details. The good news is that here, Hodor can work basically by approximating some of the linear interpolation coefficient with their expected values. And for that, you do not need to know the network. So in this case, our only competitor is uniform because network clustering does not even work. And we see that in case 2, uniform does a little better because remember that Hodor has more variance than uniform, which is what shows up in the second case, but otherwise Hodor does much better. Okay, so I'm basically out of time, so I'll just quickly summarize. So our main findings are that the network clustering based design, which has been championed over the last 10 to 12 years, it has serious issues when lurking variables are present. This is something that has been completely overlooked in the literature. We have developed a new method that can address issues from lurking variables from unknown network, and it can also correct for spillover bias. And this is something that I found really interesting, that Hodor versus the classical random allocation design has a bias variance trade-off. Our next steps are to extend this to more complicated models. For example, when different values of the lurking variable can lead to treatment heterogeneity. We next want to go to treatment. So here we just considered like a single test and a single control. But in practice, there could be multiple, the treatment could consist of multiple factors, and we will need more sophisticated models for that. We have focused on estimating the average treatment effect, and the next step is to look at hypothesis testing. Okay. The fourth point is, I mean, it looks like something you would latch on to, like on the broader impact section of your NSF proposal, but we are actually serious about this. We really want practitioners to know about our method and adopt that in use, in their practice. So we are lucky to have friends. I have some good friends who are kind of leading A/B testing efforts in LinkedIn. We also have connections to some people in Microsoft, and we are trying to convince them that this is a good idea and to see like real implementation of this in practice. And we have a preprint that I was hoping to have ready before this talk, but as usual, the semester started and my plans were over optimistic, but I hope to have that in about 2 weeks or so. So that's it from me. Thank you for your attention, and I can take any other questions that you have.
Thank you, Srijan, for the excellent talk. For the interest of time, we may ask Srijan for one question. Whoever
There's
wants
some
to.
questions in the chat as well.
Right. Maybe we can select the first one to ask. And
Yeah.
if there's remaining questions, we can stay like the Srijan can stay and the students can ask you questions. So the first question of interest is, when you use the two-stage design, how to control the time effect?
You mean when? You mean like how to determine what time should pass between the first stage and the second?
Excuse me, I just asked this question, so it's better for me to explain a little bit. So when you do the two-stage design, so basically you do one stage for the original testing group, and also for the second stage you hold out, and then within the second stage you randomize the testing for the second stage group. And I'm wondering if you design such kind of two-stage design, how to control the time effect, because the similar case in economics, they usually use difference in difference. So that's some this worries I concern about the method. But overall, your presentation is really great. Thank you.
Yeah, thank you. So this is another really great question. So yeah, so what we are assuming here is that so suppose this is like testing out a new messenger feature on Facebook. Okay? So you give, in the first stage, you have a control group and you give the messenger to a fraction of the test group. And you have a timeline for collecting data. That can be 1 week, 2 weeks, something like that.
Yes.
After 2 weeks, you are done with data collection. Okay? Now you have collected all the data from stage 1, and only now you are going to add the messenger feature to the holdout group in the test group. to the holdout subgroup of the test really. But it's a great point. So we are assuming that the spillover effect stays constant over time effectively.
Okay.
And it's a great
Gotcha.
point that's unrealistic. That should not happen in practice. So the user's engagement during the first 2 weeks of using the messenger will be different from the 3rd week or the 4th week, right? That's a great point. And yes, we should have a time respecting version of the model, which can address this concern that you have raised. Thank you. I mean, that's a
Great.
very, very good point.
Thank you. Thank you for your presentation.
Yes.
Thank you. So for the interest of time, we stop here.